basically what we do is we come up, some model reduction methods come up with a linear subspace, so they come up with some basis vectors B, and here they're written as a matrix. And we make this change of variables, so x hat has very few components compared to x. So think x is 1,000,000, x hat is 100, something like that. So you plug this in place of x, and then you ask for the equation to be satisfied in a weak sense. Okay, so you have a left inverse W for B, and you ask this sort of projection equation to hold, and that's where your reduced order model comes from these equations right here. Okay, so there's a lot of theory, a lot of algorithms, software worked out for these things. The variant, or the version of this that I'm going to focus on is called Gramian-based model reduction. I'm not going to say anything in detail about another approach, and that is an approach based on pre-lock methods. So these are the same sort of methods you use to solve large-scale linear systems and large-scale eigenvalue problems. There's a lot of work in this area. These methods can be very effective. They don't usually have as nice a properties as the approach I like, Gramian-based model reduction that results in balanced truncation. But there's a recent development in this regard called iterative rational pre-lock. So it's a rational pre-lock method. It's based on multi-point rational interpolation. And these two of my colleagues, Sergey Garrison, Thanos Antoulis, and Chris Beatty. And this does an optimal H2 approximation, and I think it's a very competitive method now. So, and we have some applications of this a little bit later. Okay, so what's Gramian-based model reduction? So here's one way to come up with a V, and this is sort of the idea behind proper orthogonal decomposition or principal component analysis. Okay, and here's how it goes. I have a dynamical system, so here we're in the nonlinear setting. It's applicable here as well. And basically, you look at the trajectory. Okay, so suppose we look at the trajectory x is tau, and we form this Gramian, and we're assuming that the system is such that this is finite. So this is just an n by n symmetric positive definite matrix where n is the number of state variables. Okay, and so I can think of taking its eigendecomposition, and I get something like this where B is an n by n orthogonal matrix, S is a diagonal matrix with diagonal entries sigma j. And typically these decay, that is, the eigenvalues magnitudes decrease. And so we can think of making a change of variables here, and writing x as linear combinations of these basis vectors. So W is a new function, and then truncating this when the singular, or when these eigenvalues get small. So it turns out these eigenvalues are really singular values of something else. So here's the way this is done in proper orthogonal decomposition. You take your favorite method and you, for integrating your nonlinear system, and you get a bunch of what are called snapshots. So these are just values of the trajectory at certain time points, and you then form a matrix X of those. And so you can think of this as an approximation to that Gramian. Okay? But if I treat X as a matrix and just take its singular value decomposition, then and then truncate it in the usual way, the matrix approximation way, that gives me a way to get a low-rank approximation to the Gramian. And the V you see here plays a role of this V that we were talking about in this. So it's an approximation to that. Okay, and so we truncate that according to the decay of the singular values. And so if we were in the matrix case, we would kind of expect a nice error bound like this. That really doesn't told. It would be nice if that held, but certainly outside the regime of where you've seen snapshots, you can't expect an approximation result like this. But that's sort of the idea, is that we think this should sort of be accurate, at least, or reasonable, at least where we've taken snapshots. Okay, so this is the usual matrix idea. This is sort of an illustration of what that means. So here's some singular values. It happens to be the singular values of an image in this case. And you want to approximate it. The matrix result says I should get a good approximation when these singular values decay. So we're going to stop at 50 there. And that gives us a reduction in the amount of data we need to represent this original m times n data. So here's the image that we looked at. So this is a matrix in terms of pixel values. And we took its SVD, and then here's a rank. We're keeping 10 terms, and that SVD gives this reconstruction. And if I add 32 terms together, we get this. And then we said we should be very good at about 50, and we see those two images are very close to each other. So you can think of that as by analogy to what we would do for a trajectory. So if you use your imagination a little bit and think of a trajectory as column by column on this matrix, so we're essentially replacing each column by a low rank approximation to it. Okay, so excuse me, drawing up. So POD has a huge literature associated with it. Here's just a few names. There are many, many others, and if I've left your favorite out, I apologize. But this is a huge literature. There's a lot going on in computational fluid dynamics. Some of the more recent developments have been in terms of trying to bring in the information from the observation. So POD, as I just described it, only worked on the trajectory. It did not take into account what you observed. And so there's been some work, especially by Karen Wilcox, in trying to incorporate that. You get this sort of idea helps you produce stable models reduced models when they should be stable, and so forth. So it makes it a lot more robust. Okay, so proper orthogonal decomposition, that's what I just described, is really related to finite element method. Both are Galerkin projection methods. The difference between the two is proper orthogonal decomposition gives you a global basis, and finite elements gives you a local basis. So if I want to see complex behavior from the finite element method, I go to mesh refinement and higher order elements, right? And what does that lead to? That leads to high dimensional systems, but sparse matrices, because the basis functions don't overlap very much. They have local support. POD is just the opposite. It finds empirically, it finds global basis functions that encode the fine scale detail that you got from the finite element discretization. Okay, so it's sort of like a spectral method, you might think, you might say. So here you get low dimensional approximations, models, but dense system matrices. So we get dimension reduction with POD, but it's ad hoc. Okay, so you have to. It's an art in how you sample to get the proper, to get a good set of basis functions and so forth. So one of the big questions is how do you automate this parameter and input sampling from POD? Okay, so what is POD and linear time invariant systems? So here you have the transfer function of the ABC system that I put up at the very beginning. And so this is what you would get for impulse response. That is, if you drove the system with an impulse at time 0 and watched the system perform, you would see this as your output, your response. And your input to state map here is given by this would be the solution for that setting. So if you look at the Gramian there, you see what might be a familiar quantity to you, this Gramian here. And so that's generally called the controllability Gramian in linear systems, and there's a similar thing, the observability Gramian also for linear systems. Okay, so for this, we can compute these Gramians in a very different way. We don't have to run trajectories. We don't have to collect snapshots. Those Gramians happen to be solutions to these Lyapunov equations. So to solve the Lyapunov equation in a reasonable way, we can work with these. And it turns out if you take both into account simultaneously, making observations and inputs important, you come up with this balance reduction. So what is balance reduction? It does this transformation, so it chooses the V and W in such a way that under the coordinate transformation you get by making the change of variables, the Gramians become diagonal and equal. And that I can't go into all the details right here for this talk, but basically what you get out of that are states that are difficult to reach are also difficult to observe. So they're unimportant, and they're cast out simply by truncation. And so the way you do this is you come up with your V and W, that's the V and W I had earlier, such that PV is WS and QW is VS. The diagonal entries of S form the Gramians in this reduced system. So for every truncation K here, you have such a setting, and you can show that the reduced order model you get from this thing right here, this setup here, is you always get, if you start with a stable system, you always get a stable system back, and there's also an error bound associated with this. These things are lacking in the pre-law methods in general. Okay, so it's a very beautiful and effective method. So you have, that S matrix, the entries of that are the so-called punctal singular values, or system invariants. And your reduced order model has an error bound of this type right here. So what you want, of course, is the output of the reduced model should be a good approximation to the output of the full order system. So they have nearly the same response characteristics. And so this actually gives you a bound on that a priori in terms of the neglected punctal singular value. So it's very much like the matrix approximation result. It extends immediately to multiple input, multiple output systems, whereas pre-law methods don't do that in a straightforward way. Preserves stability. If you just have, as I said, if you start with a stable system, you always get a stable system with that. The key challenge for these methods in the large-scale setting has been to solve large-scale Lyapunov equations. And here's, I'll talk about that in a moment. Here's what you get. This is sort of how balanced truncation works. So this is called a Bode diagram. It's the absolute value of the transfer function along the imaginary axis. And you're doing a good job with model reduction. That's the red curve here. That's the Bode diagram for the reduced order model. The better the red curve approximates the blue curve, the better you're doing. Okay, so the way this works, because of this error bound, we specify an error tolerance, and then we're able to select the order of the reduced model that will give a response that meets this error tolerance. Okay? So if I now reduce the size of the tolerance, I need a higher order model to meet the tolerance, but you see I get a much better approximation to my response characteristics. So that's the beauty of balance reduction. That's all automatic. And so here you have these punctal singular values, and this is your tolerance. So as soon as the ratio of the largest singular to constant singular value to this one falls below your tolerance, that's where you stop, and the number of singular values above here gives you the order of the system. So it's a very beautiful setup. Okay, so to solve this in a large-scale setting, I won't go through any detail at all here, but the methods we favor try to come up with low-rank approximate solutions to these systems. So this is only good if eigenvalues of Gramian decay rapidly. Otherwise, you won't be able to have a decent low-rank approximation to the solution. But often you can do this with rank k very small, and then you come up with the reduced order, the balancing transformation through these equations here. So you just take the singular value decomposition of this product and construct a transformation from these formulas, and that approximately gives you that setup that I told you was required to do balance reduction. So that's how we do it for the large-scale setting. So we're now in the situation where we can do this for very large systems as long as there's sufficient decay rate in the singular values and eigenvalues. And you can do million variable systems on high-end workstations, really, even in MATLAB. We've done that. So if you think about it in another way, this is quite impressive because these systems, these are linear systems with n squared. The number of variables is n squared. So you can really see these Liapunov equations as solving linear equations with n squared variables. And, so it's, I think, pretty impressive that you can do this. The other approach that I'll talk about later works when this doesn't. That is, this optimal H2 reduction works when you don't have the decay you need to get these Gramians, solve these Gramians. Some of the more recent activity in this area has been to apply this to descriptor systems. And my colleagues and I have worked on, there's a number of people working in this area. I'll tell you a little bit about something we've done recently. So descriptor systems are similar to what we had before, only there's an E matrix here. And so E is often singular. If E were non-singular, I could just multiply on the left by its inverse and be in the standard setting. But when it's singular, I really have to modify these methods to overcome that. And we've been able to do this for Lacine equations. I'll show you the results of that. But basically, you get very good approximation. So this is the time domain response, frequency domain response. The blue curves are the responses to the full system. Time domain, or the red, or no, just the opposite. Sorry, the blue is the reduced system, and the red is the full system. You can see it's well approximated. Okay, the problem that we worked on here was flow over a backward-facing step, and I just want to give you an idea of the effectiveness of this. This is so here we have 22,000 degrees of freedom for the full system, and we obtained a reduced order model with 15 degrees of freedom. So 22,000 degrees of freedom, 15 degrees of freedom, and the velocity profiles there are very well approximated. So this is quite an effective approach to doing model reduction for those systems. Okay, so now that's sort of background. Now I wanted to move into the nonlinear area, well, linear and nonlinear area. And I want you to know my state variables will now be y. Okay, so look for that. And this is what we've been doing in neural systems. So I've been working with my colleague Steve Cox and his student Tony Kellums. And so they're doing this neural modeling where there's The idea there is to simulate brain function by the sort of atomistic simulation. You want neurons, simulating neurons talking to each other and getting an idea of how the brain functions that way. There's two things I'm going to show you. One is linear approximations to the nonlinear equations. There are very good linear approximations, and they can get good information from that. It doesn't do exactly everything they want, but they can get a lot of information from those. And they're tremendously effective. So 160,000 variable model of a neuron is reduced to about 20 variable with very accurate response characteristics. The really fun thing, cool thing for me right now is this approach to nonlinear model reduction. And we're looking at this method that's due to Tony Padera and his group called empirical interpolation. I'll try to explain what that is. And it reduces, so we just started with this, but about a 1,200 variable problem reduced to a 30 variable nonlinear model. So here's the setting. This is what they're trying to approximate. So this is a neuron. Here's a schematic of the neuron, and these dendrites are how the neurons communicate with others. So there's a site here called the soma, and a charge builds up at the soma, and after it reaches a threshold, it sends out an action potential that sends charge along the dendrites and essentially injects current into other neurons that it's attached to. So that's how this synaptic response that they're trying to model. Okay, so here's the Hodgkin-Huxley equations that describe that activity. There, you see some nonlinearities in here. There are also some hidden nonlinearities in these alpha functions, beta functions involving exponentials. So it's a very highly nonlinear system. So their ultimate goal is to simulate a few million neuron system over a minute of brain time. That's absolutely impossible to do with the present technology. They're currently limited to about 10,000 neuron system over just a few seconds. Okay. So the model reduction that we've seen so far promises to reduce time 100 or 1,000 times per neuron. Okay, and reduce the computation time to a reasonable time. So the first, we haven't done this yet. The first goal we'll have is to simulate a 20 to 30 neuron. Like to do a simulation involving the cortex. That has about 20 to 30 different neuron types. So if we can reduce 20 or so individual neuron types, reduce more models for them, and then use those as replacements for the full order system and see how they interact. That's the idea. Try to get those to interact in place of the very expensive computation. Okay, so we think that we're at least close to demonstrating feasibility of that plan. Okay, so here I first want to show you the linearization. So this is the voltage. This is the potassium channel and the two sodium channels that you're looking at. So these are concentrations, and this is voltage at the soma over time. And you see the blue model, that's the full nonlinear system, and then there's this dashed curve here. That's the linearization. So Steve Cox came up with a very nice linearization of this. And so this is away from the firing threshold. You get a very reasonable approximate just with linear. And there's the linear pulled out just by itself. And so the green is the full linear model, and the dashed red is the reduced system. And so you can see those responses are captured perfectly. Near the firing threshold, things are not quite as good. There, the nonlinearities play a heavier role, and we really, to really make this fly, we need to capture the nonlinearities. So I'll show you what we're doing to do that as well. Okay, so I mentioned one problem with this. So we did balance that by balance truncation, but some of the problems that they're interested in solving don't yield to balance truncation because it's an example of a many input, few output system. And so the many input system, would be the controllability part, doesn't lend itself to solving these large Lyapunov equations. So you need to go to another method. And that's where this iteratively restarted iterative rational Krylov method comes in. And it's a way, so again, the details I'll be happy to tell you about after the talk, but basically there's some interpolation points that need to be found, and they iteratively update these until they get something that is optimal in the H2 norm. So it's a very good algorithm. So they here they reduced 160,000 variable neuron model to one of order 20 without using any very good response approximation. Okay. These are not expensive to compute, about 2 minutes of time to get these things. And this parameter study they did kind of gives us a verification that this is going to be effective in reaching the goal. Okay, so here's one of the models that they reduced. It's the full system is almost 7,000 variables. They reduced it to a system of order 25. And so this is the linearized model, and this is a response of for the full system in the solid line, and then there's two other graphs in there, the linearized and the reduced linearized, and you see they do very well in that regime. These are the errors. That's 10 to the minus 4 right there. This happens to be it's relative error that's reported here, and the value is small there, so it's what's causing that peak. So again, we weren't able to do balance truncation on that one, but the Conte singular values did decay, and the H2 error sort of tracks those very nicely. So that's the error when they get to a model of order 40, you were already below 10 to the minus 5. So they were in this. So to get about 3 digits of accuracy, there could be in this regime like this. Okay, this is the more demanding model, the one that went up to about 160. And again, they were able to reduce this to 20 variables. And here's the error, the approximation error for both cases, for both the 40,000 and 160,000. Very good error. Okay, so now what about nonlinearity? So we're looking at this empirical interpolation method of Padura's group, and we began with the Fitzhugh-Nagumo equations, which are a simplification of the Hodgkin-Huxley. So the nonlinearities are not quite as involved, and there's not as many different types of variables in here. And basically, you take this system, and after finite difference or finite element discretization, you come up with a system of ordinary differential equations, and that's what we're going to reduce. Okay. So if I do the proper orthogonal decomposition on this, as I started out with, here's what you get. So you get what looks like to be a nice reduction. So here's my change of variables in terms of these basis vectors. And these are my reduced variables, y tilde. But if you take a look at this, it's just as expensive to evaluate this nonlinear function as it was in the original system, because this is a big N variable vector, okay, that has to be evaluated with each component. So I didn't save anything really in the amount of work I have to do to propagate a trajectory. So that's the knock on proper orthogonal decomposition. Unless you're in a special situation where you can do pre-computation of certain quantities, this isn't really a savings. So this is what we really want. Okay? We really want to come up with a way of getting a nonlinear right-hand side that is roughly the number of variables here is the number of reduced variables, so just not much on that same order. Okay, and so that's what this empirical interpolation method can do for you. Okay, so here I'm going to describe it. So the original paper poses this in the context of finite elements, and it's called interpolation because there's interpolation at certain spatial points. It's easier for me to describe this in another framework, and that is in the framework of finite differences, where your nonlinear function in the PDE leads to a nonlinear function in the ODE of this type, where you have the scalar nonlinear function f evaluated at the discrete components, okay, of your so your y of j is your solution to the PDE approximated at point x of j. Okay? So we write down that component by component. Now we have a vector that each component is an evaluation of this scalar nonlinear function. And what we're going to try to do is approximate this by interpolation at selected components. That's the type of computation approximation we're going to try to get. So we want to approximate this nonlinear term in this fashion, where this matrix Q is a set of basis vectors that is designed to give this interpolatory approximation. So I haven't told you how to get this basis yet, but let's say we have it. The Q sub P is a selection of the rows of Q, which is a tall, skinny matrix you might think of. And so this is a square, non-singular matrix gotten by selecting certain rows out of Q. And this approximation here, so this is M, so Q sub T is M by M. There are M function components here, as opposed to N, which is very large up here. Okay, and that approximates the full nonlinear function in an interpolatory sense, and given here. So at the indices P sub I that we have selected, the full function is interpolated by this approximation. That's what it's designed to do. Okay. And so how is this a savings? So here's what we started with when we do model reduction, as I showed you earlier with the W and V. We come up with a setting like this. Here's the nonlinear term, and this is the POD complexity problem shows up here. But what we do is replace this guy by the approximation I just showed you. And then that term can be computed once and for all. So it's pre-computed. And here we have an evaluation that's in M variables, M small, very small compared to the number of state variables N. Okay? And so that matrix is pre-computed, and we just have to evaluate, we just have a number of function evaluations sort of proportional to the number of reduced variables. And how do we get this basis, this special basis? Well, we have to go and look at the nonlinear part separately. So we get some snapshots, perhaps, as we did in POD. Then we create some nonlinear snapshots specifically related to the nonlinearity, and get a singular value decomposition of that, just as we did in POD. And so these basis functions here are tailored to capture the nonlinearity. And then there's a change of basis that's given in this algorithm here. I won't go through the details of that, but basically it goes step by step, choosing the interpolation points, which components you're going to force interpolation on. And it does it by, it's very similar to a QR factorization, in the sense I want to look at the maximum discrepancy between the next U basis vector and the basis I constructed in the Q basis I've constructed so far. The maximum discrepancy is used to place the next interpolation point. So you're trying to pin down the worst case of how you were able to approximate the next U basis function in the Q basis. So it's really a change of variables, and the new basis set that we come up with is designed to be good for interpolation. Okay, so here's a demonstration of how effective that can be. Here's a nonlinear function. Here, the thing that's varying is this parameter mu. You can see it appearing here. And so we sort of simulated what you would do to get a POD basis by taking 50 values of mu distributed uniformly and that is evenly spaced in the interval 1 to pi. And then did just what I showed you on the previous 3 slides. And then used the reduced model to look at this approximation for 4 different choices of parameter. None of these were in the original snapshot set. And so the solid line is the full nonlinear function, and the crosses and pluses and so forth are the approximations. So you can see this nonlinearity, the nonlinear function is approximating very well with this. Yeah, this is an approximation of dimension 10. Okay. Now here's the solution to the Fitsu-Nagumo equations. Okay, and so the solution is a traveling nonlinear wave, so moving to the right, and here you see it at various time instances of time, moving to the right. Here you see it as a wave traveling, so I don't know which one sort of indicates how, which one can get something out of best, but perhaps this one. So the full solution is in blue, and the EIM solution is in red, and you see it's tracking that very nicely. Okay, so here's the full Hodgkin-Huxley equations. And I think just going to the pictures tells quite a story. So we did this EIM approximation there, and this is Tony Kellum's work, Steve's student. And this is the computation that he felt was really telling the tale. So we're looking at one of the neuron branches, and we're looking at this observation point right here, this node, and measuring voltage there. And there are 3 inputs coming in, three action potentials coming in. And what you should see here are 3 spikes, okay, as the various signals influence this node. And that's precisely what you see here. So the blue is the full system, the red is the reduced order model. So the full system is about 1,200 variables, and the reduced system is about This is the voltage profile at all the spatial sites along the neuron, okay, at different time steps. Okay, and there's a red curve and a blue curve there, and what you should take away from this is all across the neuron the voltages were approximated very nicely. Okay, so I'm very encouraged by this. I think this has a lot of potential for dealing with nonlinear model reduction. There are very few approaches out there that will do this. Okay. The final thing I want to talk about is this application to variation. So this is all Karen Wilcox's work. Karen and Omar, I'll have to come to the people in just a moment. But basically, it's trying to see the effect of variations in blade geometry in turbines. It's the work of these folks here. Rui Chen is Karen's student, Karen Wilcox, and Omar Gaddis. And so we want to look at the probabilistic analysis of effects of these variations in blade geometry. And the reduction is dramatic. Okay, so the idea is you want to do Monte Carlo experiments, and you want to reduce the time it takes to do those experiments. Okay, so the equations that govern this are 2D Euler equations that, after discontinuous Galerkin discretization and so forth, you come up with this setting here where R now is the nonlinearity. Okay. And W is a random vector that describes the geometric variability in the blade shape. Okay. And basically what they do is they expand these coefficient matrices, E, A, and B, in just a Taylor expansion in the different random, so we have a vector of random variables with m components, and they do this expansion just by finite differences. So this is just really a Taylor expansion, but it's expensive to compute. They do the POD reduction that model reduction that I talked about earlier, but with a twist. Okay? So they improve POD by doing what they call adaptive sampling. So it's very similar to the EIM point selection. You take a POD model and you have to do, it's a very expensive computation. You have to do optimization subject to the PDE constraint and find out where the maximum deviation is, and then you select new snapshots to add to your POD basis to improve your POD basis from those computations. Okay, so they're doing this by finding a steady state and then getting that linear perturbation off the steady state, and there's the linearization that you see here in red, and the reduced order model captures that essentially perfectly. So look at two coefficients, the lift coefficient and the moment coefficient for this problem. And this is the thing that, this to me, tells the tale. So here are the statistics, the distribution that's gotten by the full order model, full order simulation. And this is the reduced order simulation. And according to this Kolmogorov-Smirnov test that they use, these are indistinguishable, okay, in terms of the statistics that they generate. Okay, and so they did these results for about 10,000 blade geometry. Okay, and so here you can see that the mean and variance are matched very well with the reduced model. So the statistics were recovered nicely with that. But look at the time. The time to do that Monte Carlo with the full simulation is over 500 hours. And once you have the reduced model, it was only about an hour. Okay, So again, I'm impressed by this kind of reduction. The reduced model is expensive to get. It was about 11 hours to get the reduced system, but the payoff was tremendous. So I think this is yet another important future application of model reduction. It's just beginning. This area is just beginning. Okay, so that's pretty much what I wanted to tell you today. So I've tried to give you an indication of what model reduction is about, and in particular, the connection between proper orthogonal decomposition and Gramian-based methods for linear systems. I mentioned this optimal H2 reduction. If you're interested in model reduction for linear systems, this is a very promising method, especially for many input or many output systems. So I think this application in neural systems is a promising one. I think there are many other applications of this type around. It's a good area to explore, in my opinion. And the key to this is this empirical interpolation method. I think it's something we really should be looking at for nonlinear model reduction. I think it has, again, a great future. And sort of the same story for systems that have stochasticity in the system design parameters. And also, I think, greatly benefit from these sorts of ideas. So that's where I'll stop, and I'll be happy to take any questions.
Thank you very much. We have time for a question or two.
Yes.
So in the neural modeling, it seems that the reduction takes place at two levels. One is the Hudson model. It seems you are reducing that. And then when you are simulating the entire subsystem of the brain, context for example, you have n neurons there and it's truncating the complete model, you are reducing that also.
That's maybe coming. What we're just talking about doing right now is replacing the full order model of the individual neurons by these reduced models, and we believe that the reduction time just in evaluating the individual reduced order model neurons will be sufficient to at least make the first step in this. I think in the future we're going to probably have to do the next step, which is what you mentioned, do something about the interaction network of neurons as well. So we might think of aggregation techniques there, but right now we're just looking at the individual neurons.
I have a question. In one of your slides, you mentioned there is a role for parallel computing in model reduction.
Sorry?
You mentioned parallel computing.
Yes, yes.
Okay, can you say something about the role of parallel computing?
Well, so this neural model is a perfect setting for that because it's perfectly parallel, really, almost. I mean, you could do domain decomposition, for example, and the only place there would be communication is when neurons from one group actually went across and talked. You had to have a signal crossing from one domain to another, but other than that, it's perfectly parallel. So it's very. That's a good place to get more reduction, and that's already done. Okay, Tony Kellums has that so he's been working on this with the full order neurons, and so that part of it has already been done for that. So the next step, I hope, is coming very soon.
So in the previous slide, if one were to simply take a coarser model of the blade geometry that Omar and Karen Bilkoff are working on, how bad would these results be? So instead of, say, 100,000 unknowns, you simply have a model, a finite element model of a tenth of the degrees freedom.
So this system they worked on was 2D. If it were 3D, you would be in the millions of variables. They're in the 100,000. Let's see what. Yeah, you see here the number of variables is about
question was, if you simply used a coarser model, a finite element model of the blade, instead of going the route of...
Yeah. So that's where the real payoff in this proper orthogonal decomposition is. Coarse graining, so why would I do a fine scale finite element approximation only to reduce it? Well, with that was a very early slide. To get the high fidelity finite element approximation, you need high dimension. Once you have it, then you can have these. The POD comes up with these specialized basis functions that encode this fine scale detail. It's in the basis vectors then, and that's why you can. So I couldn't possibly think of just willy-nilly coming up with something that would capture all highly oscillatory behavior globally without an approach like this. And then the EIM allows you to avoid this expensive function evaluation computation. So coarse graining, if you went back up to coarse graining, you would lose the fine detail. And that's the difference. That's where I think the payoff is.
So in this particular problem, the snapshots are generated, for example, using a particular blade geometry, and those are used for obtaining, say, coefficients for other geometry. How then is a new snapshot generated without doing a full FEM?
Yeah, so that's, and I meant to say this when I was answering Anand's question as well. You can't get more information out of this than what's available in the snapshots you generated. So part of it's a very ad hoc sort of thing. You know, what I have to somehow sample parameter space well enough to see all of that possible behavior. If I don't do that, I can't hope to capture it.
My question is, you mentioned that new snapshots are generated by some kind of optimization.
Oh, this is that's what we're talking about here.
Yeah.
This yeah, right here. Okay, so where should I try to gather new data? This is an attempt at automating that. Okay, and so the way they propose to do it is to sort of I have a POD basis. I do this optimization, and that tries to tell me where to take the next snapshot. So I try to adaptively find where the next.
But the PDE is ultimately solved for getting that snapshot.
Sorry.
The PDE is ultimately solved to get that snapshot.
Oh yeah, it's very expensive. It's so this is an optimization subject to PDE constraint, and so that's you saw it. I mean, that wasn't cheap. So yeah, very expensive upfront cost.
Okay, let's thank our speaker.